Welcome everyone. Let's see the sets we use in algebra and in mathematics. The sets of numbers we use in algebra are in general subset of R, which is the set of real numbers. We use the capital R to show the set of real numbers. Our first set is natural numbers, a capital N. This set is also known as counting numbers. 1, 2, 3, 4 goes to infinity like this. How many natural numbers do we have? The answer is clearly infinite amount, right? Integers are also counting numbers, but together with opposites and zero. This part is our natural numbers, but we add a zero and we add negative sign of every natural number. Rational numbers, if we can show a number as a over b and b cannot be equal to 0, then we call it a rational number. 6 over 7, 2 over 3, 100 over 29. Irrational numbers, we show it with I. All numbers that are not rational numbers. Pi, root 2, cube root of 5, negative pi over 3. We cannot show these numbers as a over b, therefore we call these numbers irrational numbers with a capital I. Complex numbers, as we said, not all numbers are real numbers. If we are not working with real numbers, we are working with complex numbers, which are special defined, and we define them as a plus bi form. Here, a and b are real numbers, and I squared is equal to negative 1. Think of it. Try to square a real number. It will not be equal to negative 1, right? And that's called complex numbers. We can write every real number x as a complex number because of the form x plus 0 multiplied with I is equal to 0, so it can be written in this form. It follows that every real number is also a complex number. We have a really simple example. For each of the following values, identify all the number sets to which it belongs. Use the standard notations. You can pause the video and try to figure out by yourself. Listing together, negative 6 is clearly not a counting number because we don't have negative numbers. It's an integer though, and you can write this as negative 6 over 1, which makes it a rational number, and it's clearly in the set of R. Since it's in the set of R, it's also in the set of complex numbers. For 0.4, this is clearly equal to 4 over 10. So this is already a rational form, we know that. This is not equal to a counting number. This is not an integer, but it's a rational number. It's in the set of R, and it's also a complex number. Root 10, square root 10. First of all, it's not a natural number, it's not an integer, it's not a rational number. It's a real number though. My pen is glitching. And since it's not rational, it's irrational, right? So I show it with I, and it's in the set of complex numbers again. We have to be careful with this example because we know we cannot divide any number with 0. Therefore, this does not belong to any set. So we'll just say does not belong to any set. Square root of negative 5. We know that we cannot write a negative value inside this root, square root. If we do, it's not a real number. We can write this as I'm root 5, which is a complex number, so therefore root negative 5 is in the set of complex numbers. Axioms for the real number system. We will fly through these because we are used to these ideas from everywhere. Your entire life, you use these, a plus b, a minus b, you know what these are. All right, if we have a plus b, a multiplied with b, multiplied with, we don't need to write it twice. If we have a plus b, a multiplied b, these are unique numbers. Don't forget a, b, c are in the set of R. Commutative laws, associative laws, distributive laws, all of these are saying the things you intuitively know. A plus b is equal to b plus a, right? 2 plus 3 is equal to 3 plus 2. A multiplied b is equal to b multiplied with a. We also know this. A plus b plus c, if you change the order, it does not matter. Again, same for multiplying. The order does not change it. Distributive laws, you can distribute the a when you're multiplying it with b plus c, right? A multiplied with b plus c is equal to ab plus ac. Also, you can do the same thing from the right side as well. Our conclusion is clearly multiplication is distributive over addition. Identity laws, 0 plus a is a, 1 multiplied with a is equal to a. These are our special numbers. Inverse laws, if you add inverse of a number, it will give 0 to itself. If you add inverse of a value to itself, you will get 0. A plus negative a is 0. And for the multiplication reverse of it, if you multiply a with the reverse of it, you will get 1. Of course, these reverses are, this is according to addition and this is according to multiplication. Zero factor laws. For every a in the set of R, a multiplied 0 is 0. If a multiplied b is 0, then either a or b is equal to 0. Again, it's really easy to tell these, right? Negative laws. Negative a is a. Negative a multiplied with negative b is equal to a multiplied b. Again, you can change the negative sign, doesn't really matter. These are also equal to AB, so this will be equal to that. And multiplying a number with a negative 1 will change its sign. Subtraction and division. Definition of subtraction, which is quite important for us. A minus B is actually defined as A plus negative of B. And A over B is defined as A multiplied with reverse of B. And we know, again, A divided with 0 is not defined. Ordering properties. We can show positive real numbers with R plus, like with a plus at the top of R. You can see P as well in some introductory real analysis books. I saw some. Alright, which is a subset of real numbers. If A and B are in positive real numbers, then so are a plus b and a multiplied b. These are clear, right? Everyone can tell these. For every real number a, you have three options. A is in the set of R. It's a positive number, it's 0, or negative a is in R. If I don't spell this wrong, this is called tricholotomy, something like this. You can search this up. This is a really nice property as well. There's a lot of proofs based on this. But the spelling might be wrong, but I'm pretty sure you will find it if you search it. The real number line. We can represent real numbers by points on a line, right? Like the 0, 1, 2, 3, 4 goes to infinity as well, and to the negative part as well. Let's try to place these following values on the line. Square root 8. Where does this belong? Let's think like this. If I wrote square root 4 and square root 9, square root 8 is between these, right? And this is equal to 2, this is equal to 3, therefore this is between 2 and 3. Let's give it here. 2/3, let's think. 3 over 3 is 1. 6 over 3 is 2. Okay, let's not do it like that. Then let's think it like that. 0 over 3 and 3 over 3. 2 over 3 is between these two values. So therefore, we will put it like around here. It doesn't have to be perfect as long as it's is between the right numbers. Negative pi. Pi is like 3.14, it goes on and on, right? So it's greater than 3, but it's negative, so it will be around somewhere here. Let's say this is our negative pi. All right. Absolute value of a number, again, really important for us. Absolute value of a is defined as a if the inside of the absolute value is greater or equal to 0, and negative a if a is lesser than 0. Absolute value basically tells you no matter what you have inside me, it will not come out as negative. It's distance, right? Let's see some simple examples. Negative 8, for example. This is lesser than 8, right? So it's negative 8, and there's a negative sign, a minus sign in front of it, so this is 8. 3 is greater than 3. It can come out as this. All right, 3 minus 5. This is equal to absolute value of negative 2, but this is lesser than 0, therefore negative. Multiply the minus signs, this is 2. 2 minus pi. I know you cannot algebraically do much here, but what can we do is I know pi is clearly greater than 3. So which means this is clearly greater than 2 as well. Therefore, inside of this will be negative. So from that, this will come out as negative 2 minus pi, which is equal to pi minus 2. X minus absolute value of x minus 5 if x is lesser than 5. If x is lesser than 5, this is going to be, inside of this is going to be lesser than 0. Therefore, this will come out as 5 minus x as well. Last topic of today, intervals, which is really important in mathematics again. We have two type of intervals, open and closed. Open interval will tell you that that value is not included. For example, open interval from A to B tells you, let's try to imagine it on a line. Think it like this. This is our A and this is our B. It's talking about this interval, right? But a closed interval from A to B is defined as A and B are also included. Negative infinity, we can work with infinity as well. We have again open interval, we can clearly see that from negative infinity to A. So let's imagine it like this. Let's say this is our A. It's open, so it's not, we don't include it. It's going to be like this going to infinity, right? From negative infinity to infinity, open interval. All right, this is all real numbers, obviously. Think of it. Your every real number is in this interval from negative infinity to infinity. You might ask the question, what if I want to use closed interval for negative infinity to infinity? This is not correct mathematically. You will never see this form. If someone uses this form is wrong. We don't work, you cannot imagine infinity as closed form. Let's say you have an interval like this, no matter what, you cannot close the infinity. This is also mathematically wrong. We will work with open interval if it's infinity.